Welcome to physics class. Good morning, everyone. My name is Gias Uddin. My dear students, today we are going to discuss about some important numerical based on Heisenberg uncertainty principle. Today we are going to discuss about numerical based on Heisenberg uncertainty principle. Okay. So first of all, a little bit concept about Heisenberg uncertainty principle. Heisenberg uncertainty principle. The mathematical expression of Heisenberg uncertainty delta x into delta p greater than equal h card by 2 equal h by 4 pi. Okay. Where delta x uncertainty in position delta p equal uncertainty in momentum and h card is reduced Planck constant and its value, this is equal to 1.055 into 10 to the power minus 34 joules second, and h equal Planck's constant, and the value of Planck constant equal 6.62 into 10 to the power minus 34 joules second. So this is the formula of Heisenberg uncertainty principle. Delta x into delta p greater than equal h card by 2 equal h by 4 pi, where delta x equal uncertainty in position and delta p equal uncertainty in momentum. And h card is called reduced Planck constant and its value is equal to 1.055 into 10 to the power minus 34 joules second, and h is equal to Planck constants and this is equal to 6.62 into 10 to the power minus 34 joules second. Okay. And another two formula. Heisenberg uncertainty principle in terms of energy and time. In terms of energy and time. Okay. So this is delta E into delta T greater than equal h cross by 2 or h card by 2 equal h by 4 pi. Okay. So in this equation, delta E equal where delta E equal uncertainty in energy, and delta T equal uncertainty in time, and h cross is also reduced Planck constant, and this is equal to 1.055 into 10 to the power minus 34 joules second, and h equal Planck's constant, and this is equal to 6.62 into 10 to the power minus 34 joules second. Okay, now Heisenberg uncertainty principle in terms of angular displacement and angular momentum. In terms of angular displacement and angular momentum, and this is equal to delta theta equal delta j greater than equal h cross by 2 equal h by 4 pi. Okay, and where where delta theta equal uncertainty in angular displacement, uncertainty in angular displacement, and delta j equal uncertainty in angular momentum, angular momentum. Again, we can say that h cross is equal to reduce Planck constant, and this is equal to 1.055 into 10 to the power minus 34 joule second. Okay, and h equal was 6.62 into 10 to the power minus 34 joule second. This is also Planck constant. Okay, so Heisenberg uncertainty principle in terms of angular displacement and angular momentum. The mathematical expression delta theta and delta j greater than equal h cot by 2 equal h by 4 pi. In this equation, where delta theta equal uncertainty in angular displacement and delta j equal uncertainty in angular momentum, and h cross is called reduced Planck constant, and this is equal to 1.055 into 10 to the minus 34 joule second, and h is also called Planck constant, and this is equal to 6.62 into 10 to the minus 34 joule second. So this formula are very, very important to solve these types of numerical problem. That means Heisenberg uncertainties problem. Okay, so now we are going to discuss numerical problem. Okay, our first numerical problem is the uncertainty in the location of a particle, is equal to de Broglie wavelength. Okay, de Broglie wavelength. Calculate the uncertainty. Calculate the uncertainty in velocity. So this is our first numerical problem. The statement of this problem: the uncertainty in the location of a particle is equal to the de Broglie wavelength. Calculate the uncertainty in velocity. Okay, now we are going to solve this problem. Given the uncertainty in the location of a particle, that means uncertainty in the position. Okay, so delta x equal, this is equal to de Broglie wavelength, that means h by p. Okay, h by p, and delta b equal what? Uncertainty in velocity. Okay, we know that Planck constant h equal 6.62 into 10 to the power minus 34 joule second. Okay, we know that and this is equal to de Broglie wavelength, so we can write like delta x equal h by p equal lambda. Okay, we know that by using uncertainty principle, we know that delta x into delta p greater than equal h cross by 2 equal h by 4 pi, and this is equal to, we can write delta x into delta p greater than equal h by 4 pi. Okay, h by 4 pi. Okay, delta x is equal to h by p, so we can write del h by p, and delta p we can break in terms of m into delta b. Okay, so m into delta b, and this is equal to h by 4 pi. H and h cancel to each other. Okay, and delta b equal, we can write after cross multiplication, we can write m into delta b equal p divided by 4 pi. Okay, and delta b equal p into 4 pi into m. We know that p equal momentum, so p we can break in terms of mass into velocity and divided by 4 pi m. M and m cancel to each other. So we can write finally b by 4 pi. So uncertainty in velocity, our required answer is uncertainty in velocity is this is equal to b by 4 pi. So this is our required answer. For your better understanding, I am going to repeat this once again. The statement of this problem, the uncertainty in the location of a particle is equal to the de Broglie wavelength. Calculate the uncertainty in velocity. Okay. Given information, first information, uncertainty of position delta x, and this is equal to de Broglie wavelength. And as we know that de Broglie wavelength, this is called lambda equal h by p. So we can write delta x equal h by p equal lambda. And we are going to find out delta b. It means that uncertainty in velocity, and this is Planck constant h equals 6.62 into 10 to the minus 34 joule second. We know that by using Heisenberg uncertainty principle, delta x delta p greater than equal h card by 2 equal h by 4 pi, and delta x into delta p, after cross multiplication we can write m into delta p divided by p by 4 pi. Okay, and delta p equal p by 4 pi m, and p is momentum, and momentum we know that the product result of mass and velocity is called momentum. That's why you can put p equal m into b, m and m cancel to each other. Finally we get b by 4 pi. So this is our required answer. Okay, our next numerical problem is the statement of this problem. An electron confined in a box of length 10 to the power minus 8 meter. This is clear that this is a uncertainty in position. Okay, and calculate minimum uncertainty in its velocity. So solution, the given information of this question, delta x equal 10 to the power minus 8 meter, and delta b equal what? And Planck constant h equals 6.62 into 10 to the power minus 34 joule second. Okay, and particle is electron. Okay, so mass of electron equal 9.1 into 10 to the power minus 31 kg. Okay, by using Heisenberg uncertainty principle, we can write, we know that delta x into delta p greater than equal h cart divided by 2 equal h by 4 pi, and this is equal to delta x, and delta p we can break in terms of m into delta b. Okay, and this is equal to h by 4 pi. Okay, so delta b equal h by 4 pi m into delta x. Now the value of h equal 6.62 into 10 to the power minus 34, and 4 pi, the value of pi equal 3.14 into m, and this is equal to 9.1 into 10 to the power minus 31 into delta x uncertainty in position, this is equal to 10 to the power minus 8. And after solving this part, we will get, after solving this part, this is equal to 5797 meter per second. So this is our required answer. That means uncertainty in velocity. Okay, for your better understanding, I am going to repeat this once again. The statement of this question, an electron confined in a box of length 10 to the power minus 8 meter. Calculate minimum uncertainty in its velocity. Given uncertainty in position, delta x equal 10 to the power minus 8 meter, and delta b equal what? H equal Planck constant, and this is equal to 6.62 into 10 to the minus 34 joule second, and m particle is electron, so mass of electron equal 9.1 into 10 to the minus 31 kg. We know that delta x delta p greater than equal h card by 2, and this is equal to h by 4 pi. This is called Heisenberg uncertainty principle. Okay, so delta x delta p we can break in terms of m into delta b. So delta b equal h by 4 pi m into delta x. When all the values substituted in this equation, then we will get 5797 meter per second. Okay, our next numerical problem is the statement of this problem. The lifetime of an excited state of an atom is 3 into 10 to the power minus 8 second. What is the momentum uncertainty in its energy in electron volt? Okay, in its energy in electron volt, in its energy uncertainty in time, delta t equal 10 to the power 3 into 10 to the power minus 8 second. Okay, and delta E equal what? And Planck constant 6.62 into 10 to the power minus 34 joule second. Okay, joule second. And we know that Heisenberg uncertainty principle in terms of energy and time, we can write delta E into delta T greater than equal h card by 2 equal h by 4 pi. Okay, and this is equal to delta E into delta T. This is equal to h by 4 pi. We are going to find out delta E equal, we need to find out delta E equal h divided by 4 pi into delta T. Okay, the value of h equals 6.62 into 10 to the power minus 34, and the value of 4 pi, 4 into the value of pi equals 3.14, and delta T, this is equal to 3 into 10 to the power minus 8. After solving this part, we will get 0.17 into 10 to the power 10 to the power minus 31 joule. Okay. Now delta E equal, our expression must be find out in electron volt. So we can write delta E equal 0.17 into 10 to the power minus 31 divided by 1.6 into 10 to the power minus 19 electron volt, because we know that 1 EB equal 1.6 into 10 to the power minus 19 joule. So 0.17 into 10 to the minus 31 divided by 1.6 into 10 to the minus 19 electron volt, and this is equal to 1.1 into 10 to the power minus 13 electron volt. So this is our uncertainty in energy. Okay, momentum of energy. Okay. Okay, our next numerical problem is the statement of this problem. In certain atom, an electron stays in a energy for 4 into 10 to the minus 12 second. What is the uncertainty in the energy of the electron? Okay, so solution of this question, the given information of this question, given uncertainty in time. So delta T equal 4 into 10 to the power minus 12 second. Okay, and delta E equal what? Very simple problem. Delta E equal what? And H equal Planck constant. This is equal to 6.62 into 10 to the power minus 34 joule second. Okay. So by using Heisenberg uncertainty principle in terms of energy and time, we can write, we have delta E into delta T greater than equal h card divided by h by 4 pi. Okay, and this is equal to delta E into delta T equal h by 4 pi, and this is equal to delta E equal h divided by 4 pi into delta T. Now the value of h equal 6.62 into 10 to the power minus 34 joule second, and 4 into the value of pi equal 3.14 into delta T. Uncertainty in time is equal to 4 into 10 to the power minus 12. After solving this part, we will get 1.318 into 10 to the power minus 23 joule. So this is our required answer. This is the uncertainty in energy. Okay. This is our last numerical problem. The statement of this problem: what is the minimum uncertainty in the frequency of a photon whose lifetime is about 10 to the power minus 8 second? So 10 to the power minus 8 second, this is clear that uncertainty in time. Okay, so solution of the question, the given information of this question, given delta T equal 10 to the power minus 8 second. Okay, and delta nu equal what? Frequency. How much uncertainty in frequency? Okay, and h is Planck constant 6.62 into 10 to the power minus 34 joule second. Okay, we know that Heisenberg uncertainty principle in terms of energy and time, we can write delta E into delta T greater than equal h card by 2 equal h by 4 pi. Okay, and delta U we can break in terms of h into delta nu. Okay, and what is the minimum uncertainty in frequency? Okay, so this is a minimum uncertainty. Okay, so delta h into delta nu into delta T is equal to h by 4 pi, because we know that according to Planck quantum theory E equal h nu. Okay, so we can put the value of delta E equal h into delta nu. Okay, so h is constant term. but uncertainty will be associated with the frequency. So we can write delta nu equal h divided by 4 pi into 4 pi into h, 4 pi into h into delta nu. Okay, h and h cancel to each other. So 1 by 4 pi into delta nu. 1 by 4 pi into delta nu. Okay, and the value of 1 divided by 4 into 3.14 into delta nu, delta t. This is equal to delta t, and this is delta t. This is delta t. Okay, so delta t equal 10 to the power minus 8. 10 to the power minus 8. After solving this part, we will get 8 into 10 to the power 6, second to the power minus 1, and second to the power minus 1, this is called hertz. Okay, hertz and second to the power minus 1 is same thing. Okay, so delta nu equal 8 into 10 to the power 6, second to the power minus 1, second to the power minus 1, or we can say that 8 into 10 to the minus 6 hertz. For your better understanding, I am going to repeat this once again. The statement of this question: what is the minimum uncertainty in the frequency of the photon whose lifetime is about to 10 to the minus 8 seconds? This is clear that 10 to the power 8 minus 8 second is uncertainty in time. So we can write delta t equal 10 to the power minus 8 second, and delta nu minimum we need to find out delta nu minimum equal what? Okay, and h equal Planck constant 6.62 into 10 to the minus 34 joule second. We know that the uncertainty principle, Heisenberg uncertainty principle in terms of energy and time, we can write delta E into delta T greater than equal h card by 2 equal h by 4 pi. Okay, and delta E we can break in terms of h into delta nu. Okay, and delta nu equal h by 4 pi into h into delta T. H and h cancel to each other. So 1 by 4 pi into delta T. When all value substitute in this equation, then we will get 8 into 10 to the power 6, second to the power minus 1, and second to the power minus 1, this is equal to hertz. Okay, and E equal h nu, this is called energy of photon. Okay, thank you.